I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
When a physical quantity is described by a single number, such as with a unit, we call it a scalar quantity. A vector quantity is a quantity that has both a size, how far or how fast, but also a direction, which way. The size or length of a vector is called its magnitude, and we graphically represent a vector as an arrow. So everything the supervillain said before was true. The displacement vector represents the distance and direction of an object's motion, from somewhere to somewhere. It's important to see that it's drawn from the object's initial position to its final position, regardless of the actual path followed between those 2 points. It's again a change in location, just like it was before, but now the location can be in a 2-dimensional space. The net displacement for a trip with 2 legs is defined as the sum of the 2 displacements that made it up. In other words, we say what new vector gets us to the same place as the other 2 vectors put together. How do we do this? Well, we use a method called tip to tail. We draw vector A, and we place the tail of B at the tip of A, and then we draw a vector connecting the open sides. And that would be defined as their sum. The whole point here is to say, how do we end up in the same place? So if we start here, and then I go like this, and I say I want to start here and end up here, but do it in 1 step, then I would do it like that. And everything we do with vectors is going to come back to that basic assumption. Here we then define that as a sum. Right, we say that's the addition. Notice we're extending the concept of addition, and we're using, perhaps unfairly, the same symbol because it has intuitively roughly the same sense. All right, this went a little awry, but it says, given P and Q as shown, what is P plus Q? So take a moment to figure it out or sketch it out with your pen, and then we'll see where. So here again, we start with take P, and then add in Q, which is to take something which is the same length and points in the same direction. So something like that. And we can see that the sum, starting at the open endpoint, going to the open arrowhead, this is the sum. So our best answer is A. One of the things here is to keep in mind that displacement is not the same as distance. A distance is the actual physical space to which you move, but a displacement is just your change in position, really pointing from one place to another. So as an example, Anna walks 90 meters due east and then 50 meters due north. What is her displacement from her original starting point? And as we solve it, we walk through here and we say, well, Anna has 50 meters due east and then 90 meters due east and then 50 meters due north. So we have something like this, and that produces this is her displacement vector. Notice, of course, when we say the displacement vector, we're going to have 2 answers, because not enough to say how far she is from the origin. We're going to say at what angle is she at the origin. And its distance from the origin will be the length of this vector, but it's the hypotenuse of a right triangle, so we can just use the Pythagorean relation and say that the hypotenuse squared is just the sum of the sides, each squared. Or d net squared is 50 meters squared plus 90 meters squared. She's about 100, well, really 103, but about 100 meters from this. Notice that this is convenient because our 2 vectors happen to be at right angles. That isn't going to be necessary, and we'll relax that a little bit, but right now it's fair enough. How about the direction? Well, again, it's a right angle, so we can use the idea that we define in right triangles that the tangent of an angle is the side opposite over the side adjacent. So in this case, it's 50 meters over 90 meters. And that ends up letting us go down here and saying theta is the inverse tangent of that, or about 29 degrees. So together we would say that Anna's displacement is 100 meters at 29 degrees north of east. What does north of east mean? Well, if we take our sort of standard north, east, south, west axes, and we say we want to go north of east, this is east, so we mean some angle north of that. So we imagine that we say we go north of east so as to produce the thing we're looking for, and that would be the 29 degrees. Just keep that in mind. Some students find that notation a little strange, so just be careful with it. But we're literally saying we want our vector to swing north of the east line. Along the lines of displacement vectors, we also have velocity vectors. We represent the velocity of an object by a velocity vector that points in the direction of the motion and whose magnitude is the object's speed. Remember, we've talked about this before. Speed is the weird one where it's a special name for the magnitude, right? The size of the velocity. Nobody else gets their own special name for their magnitude. Generally, magnitude just means size. But here we get a special name. We say the size of the velocity vector is called the speed. And so we represent this as an arrow in the correct direction whose size is the speed of the object in that direction. This is a motion diagram for a car starting from rest, and it kind of highlights something important and interesting. Our displacement vectors are the position changing from moment to moment. The velocity vector looks much the same because, of course, we know that the average velocity is the displacement over the time. So they just scale because we're dividing by the time intervals, and we can't draw them directly on our graph. This is an example where Jake hits a ball at 60-degree angle from the horizontal and is caught by Jim. Let's draw a motion diagram of the ball that shows the velocity vectors rather than displacement vectors. And what we say is he hits the ball and it travels this way, but it's being accelerated downward by gravity, so it gets a little slower and bends a little bit. It gets a little slower and bends a little bit, and then stops, which we can't draw, and then but is moving over. So it stops going up or down, but it's still moving over. It gets bent down by gravity, and we see something like this. The next thing we do is going to just formalize this a little bit more and get it more precise.